Okay, good afternoon, everybody. Let's talk about encryption, right? First of all, let me introduce myself. I am Paolo. I'm a staff developer engineer at Nearforms and also Node Core member. I come from this little dot from Italy, which is in the middle of nowhere. The rest of it, I'll pretend we just don't exist, so that's fine. I can live with it. You can find me online on Twitter and on GitHub on those handles. And I work, as I said, for Nearform, which is an Irish, started as an Irish company, but this is now a global professional services company. We are very huge, 300 people from everywhere in the globe. We are also pretty much everywhere on NPM. There's no way we cannot find us if you use Node.js modules. I'm sorry for that. And we are always looking for the biggest talent in the world. So if you're interested, come check out for me after the presentation. I can give you good hints. And let's give credits. This talk was originally written by Michele, which is both my colleague and friend, and it was the person who was supposed to be here today. He couldn't make it, so I was sent instead. So whatever goes wrong is his fault, not mine. I'm just the deliverer of the message. I'm sorry. Okay, now, why do we need end-to-end encryption? The problem is that nowadays we store more and more and more data on the web, on digital means, pretty much everywhere, right? And we want this data to be safely stored and transferred without anybody looking at our data. The problem is that network communication are very complicated. It's not just about transferring from peer A to peer B. It's just that if the peer A is in, let's say, in Brazil, and peer B is in Tokyo, just for make an example, we have to pass through a lot of intermediate routers, links, firewalls, all kinds of devices. And each of these is a point of failure if we think about being compromised and eavesdrops by people. But without even thinking at global scale, if we stay local, wireless network can be extremely insecure. We all are now probably connected to an NDC London network, which has no protection. So anybody could listen any traffic transfer today, unless it's encrypted end-to-end. Now, if you believe in conspiracies, even LAN cables can be compromised. I could replace your LAN connector with something very nano, small, sophisticated that can temporarily record whatever traffic goes back and forth and listen to everything you said. Now, do you believe in conspiracies? I've never seen such a device, but I don't see why it cannot exist. So even physical links are a mess. Now, let's make a little test. For this one, I need 3 volunteers in the audience. Who is volunteering for this? Please. It's very simple, promise, nothing complicated. I just need somebody. 1. Come on, folks. 2. Okay, no, stay where you are. So yeah, I will come there. A 3rd one. Can you? Okay, thank you. So what I'm asking is to try to send the audience a message from the left side to the right side. That you were the one, right? And I'm going to show you how communication can go wrong even in the best way possible. This guy, which voluntarily be the 3rd volunteer, I probably will pick it up, is basically delivering the message from the left side to the right side, and that's it. That's all is going to happen. Just. Thank you very much. Okay, so he's going to tell you that he loves cupcakes. That's it. Now, of course, this was more than silly, right? But what is the point with this example? In this case, we are just talking about 3 different parties, and all of them are in bona fide. So he's a good source, he's a good destination, and he's a good network link. But anything can go wrong. Even without anybody actually listening, you can drop the message at any time. It can be an hardware failure, can be a software failure, and your data can be compromised. So this poses a problem for our subject, right? Because the data was not encrypted end-to-end, so it was plain when it exited the sources, and it was supposed to be plain when it was going to enter the destination, and this is a problem, right? So the channel was not encrypted. Now, let's take a little step backwards. What is encryption, first of all? The encryption is the act of putting information in a special code, especially in order to prevent people from looking at it without authority. This is the Oxford Dictionary, so it's pretty technologically neutral definition. The common understanding is that we encrypt the data so people without the right access cannot read the data, cannot interpret the data. Let's start with a very, very simple example. Caesar cipher. That's probably one of the most ancient cryptographic algorithm ever created, and it's very, very simple. It's just that you pick up just one parameter, which is how much you want to shift the data. So you can be -1, -2, +1, +2, and then you just make the calculation, right? So in this case, London, so L shift with a shift of +3 goes to M, N, O. Then we have the O, which goes to P, Q, and R. The N that goes to O, P, Q. The D goes in E, F, G. Then we have the O, which, as we already said, goes in R. And the N, which goes again in Q. Now, out of the blue, can you see anything wrong in this kind of algorithm? Yep, go for it.
The same letter will always become the same letter, so you can do frequency distributions.
Yes, that's exactly the point. Before getting into that, though, we're going to come back into that later. Now, trivia question. Do you know about this thing, HAL 9000? Okay, so that's from the movie 2001 Space Odyssey. Do you know where this name comes from? Go for it.
IBM.
Yes. That's a Caesar cipher of IBM with a shift of -1. So the I became an H, the B became an A, and the M became an L. So it's a widely used and known algorithm. Even more, pain for the one in the audience which is slightly older. Do you recognize this thing? If you're older like me or something? Nobody? Oh, come on. So, so this is the ROT13 algorithm. It's basically a Caesar cipher with shift of +13, and is very easy. It was used back in the 90s. I'm 1984, so I'm almost 40, right? It was used back in the day when in forums, bulletin boards, or something like that, there was no code to hide data that you don't want people to read, like spoiling, I don't know, the ending of a series back then. So in order not to just say people, I'm going to skip this amount of lines and whatever, but you always read into the screen, right? It's impossible not to look at some lines. This very basic algorithm was used not to just encrypt the data and make it secret, but not to basically mess with people that just want to skip the text without reading. It was the way. Now it's not used anymore because you can just have a accordion collapsing boxes, but back then was not possible, especially in BBS, so that's how you use it. I don't believe that you are all younger than me anyway, just saying. I'm just saying. Now, like my friend was saying over there, the Caesar cipher is very, very weak. It's by many means not a good valid algorithm because there are only few permutations possible. If you just think about the letter of alphabets, just 26 possible values for the parameter, since the -1 is equivalent to +25, so it's only 26 permutation. So brute forcing is quite easy, especially if you combine with some letter frequencies analysis. So this is an analysis of the most common letters used in the English language. So if you see that you're looking for the letter E, you can basically exploit this data to use some permutations first and see where it goes, basically. So it's very easy to brute force the Caesar cipher. It's just a very basic cryptographic algorithm. Now, what makes a good algorithm? The thing is that it's not about how it works is not about how secure it is. It's just about it must be public, and all the security lies in the parameters that you choose. Now, let me clarify this concept. The thing is that if you choose an algorithm that is secret, if the algorithm is leaked, you're done. That's it. If the security of the algorithm just stays on the algorithm himself. The problem is that you can never guarantee that something is not going to be compromised at any time, or at some time it will happen. How many times do we see that a breach in company, like I received a message yesterday of PayPal, right? Also a banking system. So you cannot guarantee that this data is going to be secure forever. On the contrary, the best is that you upfront saying, this is my algorithm. That's how it works. You know everything about it. You know every step. I'm not hiding anything to you. But I design using complex mathematics that I don't understand at all. I guarantee that if you choose the parameters in the way that I tell you to choose the parameters, and you just have to worry about those parameters to be secure, and eventually rotate those parameters often, then I can guarantee you that your system will not be breachable. Now, one thing to remember, we cannot guarantee that brute forcing is not possible, because brute forcing, by definition, is always possible. If you randomly pick a number from 1 to infinity, at some point you will get the parameter that was chosen for that encryption. Now, a good algorithm works in a way that in order for you to securely guessing that parameters, it will take centuries. And I'm not kidding, I'm speaking about literally centuries. And that means that by the time you guess that parameter, the data you were looking for is no longer an interesting data. Let's say if you were looking for a bank account, probably the bank holder was dead 200 years ago or something like that. So it's not about being resilient to brute forcing. Of course, I can randomly pick the right parameters at stage 1, but I've been really lucky. That's why we also have to rotate parameters often. But the thing is that I can brute force the system, but I will be able to success in only several hundred years. Side note, that's why quantum computing is so threatening for cryptography, because it's so much more powerful in computing time that this last sentence I've just said might be completely forfeited, because you can probably randomly pick and randomly guess a very secret parameter in much less time now. So if quantum computing goes like that, cryptography might be completely messed up and not usable anymore. Let's hope it doesn't happen, or at least it doesn't happen while we're all alive. Next generation will worry about that. That's my take there. Now, what are our choices today? The most commonly used system is the Advanced Encryption Standard, for short AES, which is a secure symmetric block algorithm that replaced the DES, that was the previous generation, that was actually compromised. One thing I forgot to tell about this, having a public algorithm also enables people to continuously validate, the good people, to continuously validate the whole algorithm is mathematically secure. That's what happened with the DES. It was actually found to be flaky, and it was later replaced by the AES. Now, the AES works by using block algorithm chiffering with a shared key. So we use is a symmetric key algorithm. Now, this means that if we want to make the communication secure, the two parties that are communicating, that are usually called Alice, Bob, the third one is usually Charlie. If Alice and Bob want to communicate, they have to agree on a shared key. Unfortunately, as you can see by definition, since we are agreeing on a shared key for crypting the data, this key is unfortunately public, right? We have to, either we agree offline on the shared key so an eventual listener cannot basically guess the key, or if we transfer the key over the net, we get the risk that somebody might actually get the key and listen to our traffic. And it's not just about listening to our traffic. Think about this. If I steal the key, as I'm a third party, an attacker, I'm able to be the man in the middle, and I can pretend to be Bob to Alice and Alice to Bob. So I can basically completely messed up the communication and gather information or transfer malicious information and so forth. So that's pretty dangerous. So the shared key in this way still goes in plain text, and anybody could steal it. Do we have a solution? If not, my talk would be over right now, right? Probably, but actually we do. Do you know these guys by any chance? Have you ever seen them? Okay. Have you ever heard of the Diffie-Hellman algorithm? Nope, not even just by the name? Yes, okay. So the Diffie-Hellman is an algorithm which allows us to share, basically to find an agreement on a key without sharing the key over the network and without prior knowledge of the key, of any parameters in the communication. There is only one, I will probably explain it much later, there is only one flaw in the Diffie-Hellman, and that's why the parameters are rotated often, but I will explain that later. But in the short, brings the security in the insecurity, because with this algorithm we can cryptographically safely share the shared key, compute the shared key. It has a strong mathematical basis, and actually the mathematical basis is very simple, very, very simple, and it uses asymmetric keys to build a shared key. Also, as I will show you in a bit, is very fast and easy to implement. So easy that I could replicate on the slides, very, very easy. And the keys can and should be rotated in each message to improve the security. Why is that? Because, as you will see in a bit, the Diffie-Hellman algorithms work on a couple of parameters that the initial party must send to the other one. Now, if a person is listening in that specific point of time, then of course it might mess the communication. But of course, it's difficult that this actually happens. Or this thing can be completely discarded if two of the three parameters that are sent over the network are pre-agreed by the parties. So let's say there is a common file system implementation that agrees on the two parameters that I will show you in a bit. After that, the party will only send one parameter that is harder to guess, and that makes the communication more secure. Now, it's time to paint. Has anybody attended the Haley talk on the colors that right after? Okay. It's by coincidence we haven't agreed on that, but it's also about colors. There is a reason for this. And actually, it was an awesome talk. Just if you missed that, watch it online when they upload it, because it was very good. So how do we generate the private and public keys? Now, the idea, and which can be mapped to colors, is that both parties agree on some common parameters, which in this image are represented by the blue color, and they have a private key, which is only known to themselves, which is for Alice the red one, and for Bob is the yellow one. That's it. Now, Alice combines the red and blue to make the public key for Alice, which is the purple one. Bob adds blue and yellow to make the green, which is the Bob public key. Simple, right? Then they exchange the public keys, and basically they send over the neck to each other. So basically, Alice sends the purple to Bob, and Bob sends the green to Alice. And finally, and that's when the magic happens, they generate the shared key by combining the other party public key with their private key in order to build the brown color. Except that that's the brown that is going to create. I haven't verified that actually those shades of blue, red and green and so forth makes that brown, but bear with me for the example. But anyway, that's the same brown. They are able to produce the same brown. That's it. At this point, they have a shared key they can use for encrypting and decrypting the next message. And after that, then can reinitiate this handshake all over again. In theory, for instance, if you're able to securely create the first shared key, you can include the parameters for the next shared key across the encrypted data. From that point in time, the communication is secure because nobody can guess that key. One thing I forgot, and I will come into this a little later when I go to the mathematical part, is that the red and the yellow, there must be so big, a number so big that nobody can safely guess them. As I was saying, they can probably brute force guess them, but after that, by the time they are able to guess them, probably Alice Bob already rotated the keys several times, so it's completely useless, unless, unfortunately, they pick up the same number, which is also unlikely. Let's make some math, right? That's time for some mathematics. Very basic, and it will pay off. Now, that color theory can be mapped to the mathematics, or actually the other way around. The mathematics behind the Diffie-Hellman can be mapped to colors. Let's see how. How Diffie-Hellman works. First of all, Alice gets to choose the 3 parameters. Forgive my calligraphy, but that's a lowercase a, g, and p for the ones that cannot read my horrible calligraphy. So they choose the 3 parameters of the communication. Now, the A is the private key for Alice. G and P are the base and modulo for the mathematical calculations. Now, as I was telling earlier, these 2 parameters might be agreed in advance in the implementation because they are not really important, because they are never rotated. The G and P are chosen once and never rotated because they are not really important. Now, Alice computes her public key, which is KA, which is created by G to the power of A modulo P. Are you familiar with the modulo operation, just in case? Okay. Now, once she has K and KA, G and P, sends KA, G and P over a public channel. Doesn't matter whether the channel is secure or not, because that's fine. The data is encrypted on the source, so we don't care. Now, it comes to Bob. Bob similarly chose B, which is the private key for Bob, and calculates in the exact same way KB, which is G to the power of B modulo P. That's it, and then KB is sent back to Alice. You remember about sharing the colors between each other, right? That's it. Now, Alice and Bob, they calculate, for Alice, she calculates the shared key by doing K equals to KB to the power of A modulo P, and Bob makes KA to the power of B modulo P. For the people that are more into maths here, you might have noticed that I use the same K in both sides. That's because they go to the same results. They are the same value. And that's where the magic happens. That's how you compute a shared key by only sharing between each other the public key. And believe me, that's how modern cryptographic systems works. Of course, they can change how the numbers are generated. They can change maybe a more sophisticated version of the Diffie-Hellman or whatever, but the principle is the same one. And the mathematics behind it is the same one. That's it, nothing else. So the math is very simple. And you can imagine that even, I don't know, in plain, I would say JavaScript with very limited device power, you can easily make a calculation like this and generate a number and eventually translate to hexadecimal and send over the network. It's pretty easy. Now, why the 2 keys computed by Alice and Bob are the same? Let's look at that. So first of all, can you see the red dot here? Okay. So first of all, let's start with Alice, but of course we could start by Bob. KA elevated 2-bit modulo P, right? Which, as we remember how we define KA, it was G to the power of A modulo P to the power of B modulo P again. By the properties of powers and modulos, it can be collapsed to J elevated to the power of A times B modulo P, which for the properties of the multiplication can be written as GB times A modulo P. That can be written as GB modulo P to the power of A modulo P, which, if you remember this, it was the definition of KB to the power of A. That's it. That's the math behind it. You can easily verify that. Basically, I just used 3 powers: the distribution of modulo, the power of power, and that's it. And the commutativity of the multiplication. That's it. Three very basic rules that we mostly learn in school can be used to make end-to-end encryption. This is insanely great, at least to me. Now, if you agree, I don't know, but to me, that's amazing. Do we want a proof? That's a proof. So let's pick A equals to 5, B equals to 6, G equals to 2 just because we are all mostly developers, so we can easily make calculation to the power of 2, and modulo P equals to 10 because I'm lazy and I would just want to take the last digit. In theory, you should not take an easy number like this, but you should use prime numbers and stuff like that, but I'm lazy, I'm sorry. So we start with Ka. G to the power of A modulo P, so it's 2 to the power of 5 modulo 10. 32 modulo 10 makes 2. That's Ka. Similarly, we have Kb, G to the power of B modulo P, so it's 2 to the power of 6 modulo 10, so 64 modulo 10 makes 4. That's it. So these are the two letters, right? Now, if we try to compute K, basically we have, by shorting, we have 2 to the power of 4 modulo 10 makes 16 modulo 10 equals to 6. Or if we start from Bob, we have 4 to the power of 6, which makes a modulo 10, which makes 4096 modulo 10, that makes 6. Black magic. That is just math. That's just it. And that's how it works. Now, usually I like to close my talks with very, very smart quotes from people. In this case, I just found one from Whitfield Diffie, that's that Diffie, that says the decision we make about communication security today will determine the kind of society we live in tomorrow. In other words, if we did not embrace end-to-end encryption, going into the future, since we store more and more of sensitive data, sensitive for people, just let's say private communication between friends, family, and whatever, or health data that can be used by evil corporations, or even government security, right? If we don't pay attention on how we communicate this data can finish in very horrible ends, and all the worst can happen. So once again, if you believe in conspiracies, I don't, but in this case, I should probably. Horrible things will happen to people, to countries, and to probably the entire world. So we have to be very, it's not that everybody should understand how end-to-end encryption works, but we should understand why we need it and what is a good thing when we have it. And for instance, we should not complain if we cannot unlock our data at Apple if we forgot our password, because Apple cannot access that data anyway. And that's a good thing, because if they can do horrible things with that. So that's the problem, right? And that's it for me. Do you have any question?
How smart are the 5-year-olds in Italy?
How much?
How smart are the 5-year-olds in Italy?
I mean, I have a 3.5 daughter, which is way smarter than I remember to be when I was her age. So it's increasing. It's increasing a lot. I can tell. Anyone else? Okay. If anything comes up later, you can find me wandering around. So ping me at any time. One last thing, I was told to remember you that you should, if you want, leave a feedback for the presentation when you exit the room. And for the rest, thank you very much.